All right, let's take a look at the agenda. I usually start every lesson every lecture with the agenda, just to point out where we are so far. So today, obviously, a lot of introduction. We'll jump into material soon enough with data modeling, UML, data definition, tables, foreign keys, primary keys today. But we'll also go over the first assignment that won't be due for another couple weeks. Usually the assignment obviously is based on that material that we covered in that particular lecture. So you'll notice the first couple of weeks is it's fairly theoretical. First we'll see that we'll be talking a lot about the relational model, but using relational databases since it has been and will be for a while the most common way that we represent data for long-term storage. And But we'll try to be a little bit more abstract, and we'll introduce graphical ways of representing it using UML, ER diagrams, irrespective of what actual technology you're using to store the actual data, which will allow us to think about it in a conceptual way, right? So that we can be independent of the actual mechanism for storage, and where relational database is just one particular way of storing data. But there's certainly many others, right? You can store using XML, it can binary, or JSON, or comma separated values, or whatever, right? Whatever you decide to store it. So we'll do UML today. We'll talk about we'll start this week, but we'll finish next week on some of the something that we'll be drilling into you for quite a while, the whole semester, perhaps till the first half of the semester is avoid redundancy. Avoid redundancy. That the data there should be one only way that the data is represented in your database, and the reasons that we'll keep saying is that redundancy breeds inconsistency, right? If you have two watches that conceptually should always have the same value, it doesn't really matter which one you read, right? But your problems might occur that the two watches actually start drifting apart from each other for whatever reason. That the reality doesn't match the conceptual expectations that these two values should be the same, right? There would be no reason for these two watches to be different. But nevertheless, in reality, for whatever reason, things drift apart, right? And whenever things drift apart, then you don't really know which one to trust. Is it this hour or that other hour, right? So usually inconsistency diminishes the value of whatever it is, the data that you're looking at, right? Because you can't trust it anymore, right? So we always look to remove redundancy. Instead of two watches, I'd rather just have one, and always trust that watch, right? And all my decisions are based on consistently wrong data. No, well, ideally whatever data we're storing, it represents some real phenomena in the real world, right? That accurately represents it for us to do whatever business decisions that we can forecast, production or prices or whatnot, that we can make educated guesses at based on real data. So us as information technologists, right? We are the keepers of this information that it should not be distorted or accessed by the wrong folks, and it should be always available, and it should be trustworthy. So we'll talk about normalization, functional dependencies, and whatnot for identifying possibilities of redundancy. Why do redundancies occur? Right, that we might have read a sentence wrong, right? Or there might be a requirement, right? That from the specs, and us as engineers, we always have to be aware of these requirements, that we shouldn't take them at face value. We should always question or push back or challenge requirements if we know that those requirements might be introducing redundancies or certain constraints that might be diminishing the overall quality of the data. So yeah, so always question requirements. We're part of that process, right? Of making sure that requirements is what needs to be done. We'll start SQL about the second, third week, and we'll spend a couple of weeks on doing SQL, mostly queries the first week, week three, third week. So a lot of SQL queries and joins and doing all sorts of clauses, having and unions and whatnot. So we'll spend about a week there. We'll come back the fourth week and finish up with updates, inserts, and deletes, as well as store procedures where we can program right inside of the database. We'll start introducing in week 6 or 5 programmatic ways of interacting with the database, right? So the first 5 weeks is us, in front of the database and interacting with some kind of client, yes, directly accessing from a client. We'll start creating different layers of abstraction. Well, I mean, the database already is an abstraction layer, right? There are no real tables. That's just an abstraction in a particular way that we find it very convenient of thinking about the data, right? They're not real tables and not real records, right? It's just a layer of abstraction that we conceptually build on top of whatever actual binary representation we have. So we'll build other abstractions, right? That's what we are. Humans are abstraction machines, right? We just keep layering abstractions on top of abstractions. The first abstraction we'll look at is interacting with a programmatic language. We'll use Java the first time around. So we'll introduce JDBC and we'll talk about some of the security and concerns whenever we are receiving data from programmatic systems where folks are filling out forms and providing that data that could be malicious, right? And how to protect against that, how to clean up and clear out any malicious code or characters and whatnot. We'll then introduce another layer of abstractions and say, well, I don't really want to. Every time we find we feel comfortable in a particular technology, we start finding patterns, right, of things that are repeatable. And as good software engineers, we are very lazy. Whenever we find something that's repeatable, we want to automate it. Well, I don't want to do this ever again, right? I'll create some functionality or template or that can automate a lot of this for me. And we'll see some of that when we use JDBC. We'll identify patterns, right? We'll do a couple of data access objects. It's a design pattern, very common design pattern on encapsulating or modularizing the data access layer from the programmatic layer. And then once you've done 2 or 3, you'll identify, hey, wait a minute, there's a pattern. They all look the same, right? And we'll say the only thing that changes might be the name of the table, the fields, the data types, and could I automate this somehow, right? Maybe I can create some kind of generic DAO, right, data access object that I can programmatically configure, and that's what the object relational mapping discussion will be about, right? That there are quite a few vendors that already provide this kind of plumbing, right? That once you've written a couple of DAOs, you've written them all, right? So how could we configure these? So we'll spend a week or so with the Java persistence API. Again, the focus here is using Java, but even though we're using Java, the concept is equally applicable in other object relational mapping in other languages or other infrastructures, right? So .NET has its own, and Python has its own ORM, and whatever language you can think of, will have an ORM solution. Okay, so but they all address the same kind of concepts, right? Mapping some object relational, object representation as classes and whatnot to mapping to some infrastructure, whether it's relational or non-relational, right? In this particular case, we'll look at Java's solution to this, which is fairly mature as a solution, and it's a good place to get started. So after that, we'll have the midterm. So yeah, the midterm will be the entire class. So obviously there'll be no lecture that week. We'll then come back and talk about, again, another level of abstraction. Is that you have this data, this raw data that you've been accumulating over the years. Maybe you have a lot of legacy data that your business has accumulated over decades. Maybe they have it behind some really old infrastructure, but nevertheless, it's data, right? That data usually has value within the organization, but folks might be considering ways of monetizing that data, allowing folks to integrate that data with other folks, right? And so we'll talk about strategies where these data centers can be integrated with other systems. There was a big boom towards the big bust, .com bust, where everybody was thinking that web services was gonna bring on world peace, and then everything fell apart. Nevertheless, we learned a lot back then, and the technology has survived, and today is very it's heavily used in technology. So we'll spend some time there. We'll see how that data models can be represented or mapped into other technologies. We'll talk about RESTful representations of a data model. We'll spend a week or so. This probably will spill over. We'll talk about MongoDB as one particular implementation of the NoSQL that has become very popular today. Trying to solve new types of problems, right? This big explosion of huge data sets, right, that are not necessarily relational, right? That usually is data that we don't know what the structure is, right? Relational databases assumes that you know the structure, right? That you know how records are related to one another and how you can split it into entities, but today a lot of the data that is being collected, oftentimes there is no data. The data needs to be discovered, after the facts, right? Every time you wave your phone, you're creating a huge stream of data that somebody's storing somewhere, right? And that they're trying to relate your phone with everybody else's phone around here, right? And they can determine who's paying attention or not in this class. And they can do all sorts of data analytics and find what those relationships are that are not necessarily in my stream of data, right? How is my stream of data related to somebody else's stream of data in the same room? So we'll talk about non-relational databases, right? That for collecting this unstructured or at least the structure can be determined later. Right, what the relationships are, and so it's malleable. The structure is malleable, right? It can change over time, and in particular, we'll use MongoDB that allows us to store data in a JSON format, which has been, it used to be that XML was the most used way of transferring data amongst systems that integrated systems, and JSON has overtaken XML only because the particular circumstances of web technology has exploded, and everybody, and so JSON is one of the more common and convenient ways of exchanging data. We'll do some light web programming. Usually folks I've tried to use other frameworks, phones or mobile UI using Java Swing, but most people ask me that they would prefer to do something web. So we'll do some really light web, enough to just display some data on the screen and interact with it, but very light. Okay. Let's see. We'll talk about other ways of storing data. We'll talk about XML in particular, where we have a hierarchical way of representing data and transforming data. Oftentimes happens that between data systems, there has to be a transition or conversion of the data and how it's represented in one in one enterprise that it's interacting with some other enterprise, right? It might be Ford Motor Company interacting with all their providers, all the different vendors, all the different car dealerships, right? And they all have their own databases. They have their own particular representation of what a car might be. In a university, a car might be just a license plate, and that's it, right? But from Ford Motor Company, maybe a car might be a little more involved, right? On how many doors, the windows, and the seats, and whatnot. And a car dealership might be only the customer and the. So it depends on which domain and who is using the data. They might have their own representation of the same concept, right? And they might have their own schema, their own data types, their own structure. And oftentimes, to have these systems integrate between them, you have to do all sorts of conversions, migrations, and transformations of the data, between different representations of the same concept. So we'll talk about that, how to do XLT transformations of different XML documents. In all of these, in non-relational databases, in XML, we'll always circle back that the same concepts the same challenges that we saw in relational databases, redundancy, normalization, all those same challenges that we had in relational databases, are still with us, no matter what form representation you're going to be choosing, right? Whether it's non-relational or XML hierarchical or spatial data, it's the same challenges, right? Of redundancy, inconsistency, and normalization. Okay. So that will come back. We'll then talk about transactions where multiple users might be using the same data set, accessing the data concurrently, right? That you might have hundreds of folks asking for the same type of information and trying to make modifications and if you've done any multi-process programming, you might have been exposed to the challenges of what do you do when you have shared resources, right? And all sorts of inconsistency if you have multiple threads that are accessing the same data. How do you synchronize all these folks that are trying to access the same data, right? So a lot of that will come back here that is applicable to relational databases. So we'll talk about how to deal with transactions. We'll also talk about indexing, on how is that can we optimize performance of databases, on seeing how are folks accessing the data, right? And, can we organize the data in such a way that we can optimize those queries, right? So we need to identify what are the most common queries, which indices do we want to add to tables. We'll see that indices not necessarily is the panacea, right? It might be that if you add indices, it might actually backfire. You might have worse performance, right? So we'll see where it's applicable, right? Where it can help, and where indices might not help. All right. So we'll see those edge cases, and also see how we can tweak and tune certain queries that can perform better depending on how they're written. So that's the Wednesday. Well, wait a minute. No, wait a minute. That can't be. I think these are flipped. The final exam will be December 4th when we come back from Thanksgiving. Right. So that week, that Wednesday, November 7th, I believe there's no class. That's the Wednesday Thanksgiving. There's no class that Wednesday. So right after Thanksgiving, we'll have the final exam. Okay. And a week after that, we'll have the project evaluation. That week, the TAs and myself will be somewhat unavailable. We'll have that last week of the semester to grade all the projects. So if you need help, please come to us much before that. All right.